In this video, we're going to introduce two series convergence tests, the ratio test and the root test. These two tests are particularly useful because we'll be able to determine the convergence or divergence of a series based solely on the terms of our series, and we won't have to compute any integrals or find another series to compare our given series to or anything like that. We'll be able to just use the given terms to determine the convergence or divergence of the series. We'll start by discussing the ratio test. In order to motivate the ratio test, we're going to recall the basic structure of geometric series. So recall that a geometric series is a series of the form sum n equal 1 to infinity of a times r to the n minus first power. Here a and r are just two real numbers. If we want to write out some terms of the series, the terms would be a plus ar squared, plus ar cubed, and etc. In this series, if we want to consider the ratio of two consecutive terms, we see that this ratio is always going to be the same. So if I pick any term in this series, maybe the term n plus 1, we're going to get ar to the n, and I want to take the ratio of that to the previous term, which will be ar to the n minus 1. And when we simplify this, the a's will cancel and most of the r's will cancel, and what we're left with is just the number r, which is just a fixed constant in a particular geometric series. Now we know the value of this number r will determine the convergence or divergence of our geometric series. Specifically, if the absolute value of r is less than 1, then we know this geometric series is going to converge. And if the absolute value of r is greater than 1, we know this geometric series is going to diverge. We also know what happens when the absolute value of r is equal to 1. The geometric series will diverge, but we're going to omit that fact for the moment and focus just on what happens when the ratio of terms is not equal to 1. Now, this same reasoning here actually will work with any series with non-zero terms. Instead of thinking of r here as just a fixed number from the geometric series form, if we think of r as the ratio of terms, this idea extends naturally to any series. We can always take the ratio of two consecutive terms. We can actually take it out as far as we want in the series by letting n go to infinity as a limit. And we can see if we have one of these two conditions, and that is if the ratio of terms is less than 1 or greater than 1. And if that is the case, then the series that we're analyzing will either converge or diverge respectively. And so the ratio test puts all of this into a formal convergence test that applies to any series with non-zero terms. So for the ratio test, we're going to look at any series with term a sub n, as long as a sub n is non-zero. So this could have all positive terms, it could alternate positive and negative terms, it could all be negative or anything else, as long as the terms are non-zero. We're going to define this number r to be the limit as n goes to infinity of the absolute value of a n plus 1 divided by a sub n. This quantity inside the absolute value is just the ratio of two consecutive terms in our series, the n plus first term divided by the nth term. We take the absolute value to give us a positive value there, and then we take the limit as n goes to infinity to account for taking this ratio very far out in the series. When we compute this limit, we have this number r, and the value of r will determine the convergence or divergence of our series by the following rules. If the value of r is less than 1, then the series will converge. If the value of r is greater than 1, then the series will diverge. And if the value of r is equal to 1 exactly, then the test is inconclusive, and we will need to use some other test to analyze the convergence of that series, because it's possible for the series to converge and have a value of r equal to 1, and it's also possible for a series to diverge and have a value of r equal to 1. It is worth noting that these first two conditions, when r is less than 1 and r is greater than 1, are exactly the same as they are for the geometric series. When the ratio of a geometric series is less than 1, then the series will converge, and when the ratio of a geometric series is greater than 1, the geometric series will diverge. To see an example of how the ratio test can be used, let's determine whether the series n equal 1 to infinity of n squared over 5 to the n converges or diverges. For this series, we notice that a sub n is our general term, which is n squared over 5 to the n. And this means that the n plus first term, a n plus 1, will be this same formula with n plus 1 substituted in for n, which will give us n plus 1 quantity squared over 5 to the n plus 1. In order to use the ratio test, we want to compute the value of r, which is the limit as n goes to infinity of a sub n plus 1 divided by a sub n. Notice we're omitting the absolute value bars here in this example because the terms of our series are all positive and the absolute value will not do anything. But if we did have, say, a negative 1 to the n or something like that, we would want to include that in order to get rid of all the negative values in our series. In this case, we can just simply substitute in our values for a sub n plus 1 and a sub n. So a sub n plus 1, we have n plus 1 quantity squared over 5 to the n plus 1. And instead of dividing by a sub n, we're going to multiply by the reciprocal of a sub n, which is 5 to the n over n squared. Now we just need to compute this value. So we can rearrange this. We can put these squared terms together. So this would be n plus 1 squared over n squared. And we can put the 5 to the exponential terms with 5, base 5 together. So 5 to the n over 5 to the n plus 1. Right? And these things simplify pretty nicely. We get the limit as n goes to infinity. This first term we can rewrite as n plus 1 over n, quantity squared. The second factor here, 5 to the n over 5 to the n plus 1, this actually becomes 1/5 because we can cancel 5 to the n in both expressions, and we have one factor of 5 remaining in our denominator to leave the 1/5. Right. Now this first term we can keep rewriting if we wanted. We could divide everything by n in there and we get 1. We can actually expand or simplify this fraction. We have n over n, which is 1, plus 1 over n squared times 1/5. And we know as n goes to infinity, we know 1 over n will go to 0. And so this limit here will go to 1 times 1/5, which is just 1/5. Right? So our value of r for this particular series is 1/5, which we know is less than 1. And since our value of r is less than 1, our series is going to converge by the ratio test. If this number r, if this limit had been equal to 5, then we would conclude that the series would diverge by the ratio test, since we'd obtain a ratio of consecutive terms whose limit is bigger than 1. With the ratio test, we looked at the limit of the ratio of consecutive terms of a series and used that value to determine the convergence or divergence of the series. There's another approach that, instead of looking at the limit of the ratio of consecutive terms, involves looking at the limit of the nth root of the nth term of the series. And the analogous test by looking at this quantity is called the root test. And it is nearly identical in structure to the ratio test, except here the number r that we're going to use to determine convergence or divergence is not determined by a ratio of terms, but rather by the root of the terms. So here for the root test, we again have a series a sub n with term a sub n where we have non-zero terms. And r is now going to be the limit as n goes to infinity of the nth root of the absolute value of a sub n. So we take our nth term, we take the absolute value to make sure it is a positive number, and then we take the nth root, and then take the limit as n goes to infinity of that quantity, and that is our number r that we're going to use in this test. The conclusions of the test are exactly the same for as they are for the ratio test. If r is less than 1, then our series will converge. If r is greater than 1, then the series will diverge. And if r is equal to 1, then the test is going to be inconclusive, meaning the series could converge or diverge, and another test is needed. It is incredibly useful to notice that the statement and conclusions of the ratio and root test are only different in how the number r is determined. For the ratio test, it is the limit of the ratio of consecutive terms, and for the root test, r is the limit of the nth root of the terms. To see an example of how to use the root test to determine the convergence or divergence of a series, let's consider again the series n equal 1 to infinity of n squared over 5 to the n. You might recall that just a few moments ago, we showed that this series converged using the ratio test. Here we're going to show that it converges using the root test. In order to use the root test, we need to compute this number r, which will be the limit as n goes to infinity of the nth root of our general term, n squared over 5 to the n. Here we are again omitting absolute values because our terms are always positive. And so we need to compute this limit. Here, one approach would be to break up the nth root of a fraction into a fraction of the nth roots. So we can take the nth root of n squared in the numerator and the nth root of 5 to the n in the denominator. In the numerator, a common property of exponents can be used to rewrite this as the nth root of n all squared, so we can bring that squared outside of the radical. And in the denominator, we have the nth root of 5 to the n, and that simplifies just to 5. Now, we might recall an important and commonly occurring sequence that the limit as n goes to infinity of the nth root of n is going to always equal 1. So this sequence here, the sequence nth root of n will always converge to the number 1. And so here, with all the properties of exponents that we've used, we've essentially broken this problem down to this particular limit. And so this limit will equal 1 squared over 5, which will be 1/5. And 1/5 is less than 1. And so here we've taken the nth root of our general term, taking the limit as n goes to infinity, and obtained 1/5, which is less than 1. And therefore, this series will converge by the root test. And so here, now that we've done this example, both using the ratio and root test, we've seen in two different ways that this series will converge. And in both cases, we've seen that in order to do this, we simply need to compute a limit, either of the ratio of consecutive terms or of the nth root of the nth term. And it's probably up to everybody individually to decide which one of these two approaches, which of these limits is actually easier to compute, although they are pretty similar in difficulty. But in this case, either test works fairly well to determine the convergence of this particular test, and it's just about being able to compute this limit, either of the ratio of consecutive terms and use the ratio test, or of the nth root of the nth term and use the root test.